Swayam Prabha. Digital India. Educated India.
Before we talk about randomized algorithms in linear algebra, since many of you may not be familiar with the concept of randomized algorithm, I would like to provide you simple examples of randomized algorithm to solve simple problems so that you can understand the power of randomness to solve problems, and then we will get into solving large scale problems in linear algebra using randomized approach. So randomization or randomized algorithm. Deterministic algorithm give exact results on all instances of a particular problem. So what is an example? You have the standard matrix multiplication, matrix multiplication, that is a deterministic algorithm. We have the inner product based algorithm that can compute any and every matrix so long as the number of columns of the first matrix is equal to the number of rows of the second matrix. That's called condition for compatibility of multiplying two matrices. So when I say a matrix multiplication problem is a class of problem. There are matrices of size m by n, there are matrices of size n by p. I would like to multiply matrix A of this size by matrix B of this size. Here m, n, p, they are all integers. M, n, p, three integers can take infinitely many values. So there are infinitely many instances of the matrix multiplication problem. The matrix multiplication algorithm helps us solve the problem of multiplying any two matrices of size m by n and n by p. So that's all instances. It gives exact result. It's a deterministic algorithm. That there's nothing random. The complexity of solving any problem is always related to the worst case analysis. In the case of matrix multiplication, n cube complexity is the complexity of multiplying two matrices. Randomized algorithm use one or more random moves or choices in an otherwise deterministic method. So how does an algorithm becomes randomized? Because during the course of an algorithm, we try to consult a random number generator by tossing a coin, by throwing a dice, or generating a random number using a piece of program to make certain choices. Once you make the choices, the rest of the algorithm may be deterministic. So randomized algorithms use one or more random moves or choices in an otherwise deterministic method. These algorithms may behave differently when run on the same input. So that's the difference in here. If you don't change the input, if you run the algorithm on the same input several times, deterministic algorithm will give the same result. Randomized algorithm, because of this consulting with a random number generator, because you are trying to consult a random number generator such as toss of a coin or throw of a die, no two times the throw of die gives the same result, no two times the throws of a die will give the same head or tail. They may change. There is a probability of that. Therefore, we cannot expect the randomized algorithm when we repeated that algorithm to give the same result on when we run the same input, but different times may give it to different results. So what is the randomized algorithm? It makes randomized moves by consulting a random number generator. Please understand, a good random number generator is toss of a coin. Another good random number generator is a throw of a die. but random number generated by toss of a coin can give you only 0, 1 or minus 1 plus 1. The throw of a die can give you only 1 to 6. 2 throws of a die will give you to 1 to 36. But these number ranges may not be enough. So we would like to be able to have access to more powerful random number generators. So these random number generators are driven by algorithms. So we are going to talk about random number generators themselves. Algorithms work well on typical instances. Under a suitable assumption on the input distribution, we can compute the average case analysis. On an average, how much time it is going to take to solve a problem using a randomized algorithm. These are some of the concepts that are used within the context of randomization. So the question is, what constitutes a good distribution for picking the random moves? And that comes from the performance measure. One performance measure is expected or average running time. But we saw that on the same input, different times you run, it may follow different paths, it may take different times. So we are interested in what's called the expected or the average running time. Another measure is, what is the probability the algorithm will terminate in certain number of steps? I can specify the number of steps, and I would like to ask myself the question, what's the probability the number of the algorithm will stop in certain number of steps? So you can see that the behavior of the random algorithm is random. So the time it takes to be able to compute is a random variable. Computing the distribution of this random variable may be difficult. So we are interested in expected time. We are also interested in what is the probability that this time is no more than basic number of steps. I want to tell you, many of the parallel games, for example chess, the rules are deterministic, but the evolution of the chess is anything but deterministic, is random. If the evolution of chess is going to be deterministic, I should be able to predict the evolution of chess. If I can predict perfectly the evolution of chess, then there will be no interest in chess. People are still trying to master chess. Same thing in football. The rules of the games are fixed, but the evolution of the game is anything but deterministic. Bridge, rummy, any board game. So the rules of a board game or any other parallel games or any other game are deterministic, but the evolution is random. So randomness is all around us. And when we want to choose between A and B, we toss a coin and then decide A and B. When two teams want to start playing a football game, the umpire tosses a coin, and depending on the result of the toss, he says team A has the ball first or team B has the ball first. So our trying to use random number generators to decide which game to start is rather usual. So that's randomization comes into play. Evolution of any game is random. So randomness is all around us. But in computer science, we are interested in deterministic algorithm. So why do we go from deterministic to random? There are probably a couple of reasons. One is, if the deterministic algorithm takes long time, I may be able to randomize and get approximate solution to a hard problem in a lesser time. So randomization is a pathway to be able to get good approximation in reasonably good amount of time. There are two fundamentally distinct pathways to randomization. One is called the Monte Carlo type, another is called the Las Vegas algorithm. The Monte Carlo type algorithm, what is the property? It always provides an approximate solution. The quality of approximation increases as the number of samples used increases. It was originally developed to numerically evaluate the multiple integrals with the complex integrand in the 1940s at the Los Alamos National Lab. During the Second World War, Japan has attacked America. So America was pulled into the Second World War. Until then, they did not. So they wanted to teach Japan, so they developed the atomic bomb. Hiroshima and Nagasaki happened. So during the process of development of the atomic weapon, please understand, I am not advocating atomic power, atomic weapons, but I am talking about a piece of history that happened. So eminent mathematicians and scientists at the Los Alamos National Lab were working on this sacred project. No one knew, but a few group of military people and scientists. They were involved in trying to compute complex complex mathematical expression, evaluating complex integrals in the context of design of nuclear bombs that involve multiple integrals with complex integrand. Necessity is the mother of invention. Von Neumann and his colleagues working in the Los Alamos National Lab, they invented this notion of random number generator. They invented this notion of Monte Carlo method. They exploit the power of the Monte Carlo method to be able to numerically evaluate integrals with complex integrand. That's the historical starting point. So it started in the 1940s. Classification of randomized algorithm again continues. Another is a Las Vegas algorithm. Las Vegas algorithm never returns a wrong answer, but it may take forever to get the right answer. It was introduced by Baba in 1979 as an alternative to Las Vegas algorithm. Most of the algorithms that we are going to be talking about in the context of randomized linear algebra are of Monte Carlo type, where the quality of approximation is a function of the number of samples. But it's good for you to be able to understand the difference between the basic approaches to randomized algorithms, Las Vegas type and Monte Carlo type. So what is the primary distinction? Monte Carlo type gives always the result. The results are approximate. The quality of approximation increases with the number of samples. Las Vegas type, on the other hand, never returns the wrong answer. It returns the correct answer, but it may take forever to be able to return the correct answer. So this is the fundamental difference. So you can design randomized algorithm in one of two ways. Numerical linear algebra exploits the Monte Carlo method. So we illustrate both the cluster method by one example for each. Before that, we need to understand the basic algorithm that are used to generate uniformly distributed random integers in the interval 0 to 1 for large n. So for the sake of completeness, I am going to spend few minutes on trying to tell you how to generate random numbers, random integers, random real numbers in practice using computer programs. So random number generation. Let m be a large integer. In general, m in the case of 32-bit machines, the standard 32-bit machine, m is going to be 2 to the power of 31 minus 1. Why is that? There are 32 bits, 1 bit is always reserved for sign, rest of 31 bits. The largest integer that can be represented in a m-bit machine is where m is 30, where the length of the word is 32 bits, m is 2 to the power of 31 minus 1. So that's a lot. So generally m equal to 2 to the power of 31 minus 1 in standard arithmetic on standard machine with 4 bytes for the word. Let a be a positive number, that is a relatively prime to m. You should know two numbers are said to be relatively prime if the greatest common divisor between them is 1. That's called the GCD, greatest common divisor. GCD of 6 and 3 is 3. GCD of 6 and 5 is 1. So if you consider the numbers 1, 2, 3, 4, 5 with respect to 6, 2 divides 6, 3 divides 6, 4 and 6 have a common divisor. 6 and 5 are relatively prime. 2 is not relatively prime to 6, 3 is not relatively prime to 6, 5 is not relatively prime to 6. Prime You have a number said to be a prime if it is divisible by itself and by 1. Two numbers are said to be co-prime or relatively prime if their GCD is 1. So pick a number A whose GCD with respect to m is 1. Let C be a large integer. Let x naught be another large integer. X naught is called the initial condition. You can express your initial condition as your date of birth. That means you can say month, day, year. So you can express it, or your telephone number. You have a 10-digit telephone number, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it could be a 10-digit number. It would be your date of birth. So this could be utilized as the initial condition x naught. C is another large integer. C is called the offset parameter. A is a multiplying factor. So A, M, C and x naught, given this, I have a formula now, I have a recurrence relation, xn plus 1 is equal to 8 times xn plus C mod m. The modular arithmetic, I am sure you all have some familiarity with modular arithmetic. 8 times xn plus C, A is relatively prime to m, C is positive. So this can generate numbers starting from x naught. So if you have x naught, given A, given C and given m, I can compute x1 from x naught, x2 from x1 and so on. So this generate a sequence x1, x2, x3. And what is the idea? If m is large, if you start x naught with large, A is large, the sequence so generated behaves like a random sequence of integers in the range 1 to m minus 1. So I am going to give you a small exercise. If you pick m is equal to 11, A is equal to 3 and pick x naught, your own choice, set C is equal to 0. So C is 0, A is 3, m is 11, x naught is equal to a number in between 1 and 11, 1 and 11. Apply these to this and use a pencil paper, try to compute these numbers and see how the numbers 0 through 11 arrange themselves. The order is not regular, the order looks random. That's why it's called the random integer sequence in the interval 0 to m minus 1. Since the recurrence relation that generates it is a deterministic device. Its output looks random, it behaves random. Therefore, the random numbers generated by this are called pseudo-random sequence. All the computer-based software program generates only pseudo-random numbers. But if you have toss of a coin or a throw of a dice, they are pure random. Since we need larger number of random integers available for our calculations, we are going to give up the true random to settle for pseudo-random. We are able to compute them. So on a 32-bit machine architecture, m is 2 to the power of 31 minus 1. Using this in 1, we will get a maximum possible of what is the value of 2 to 31 minus 1? It is this number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This 10-digit number. So the maximum number of numbers you can generate is 1 to 2 to the power of 31 minus 1 in some random order. Therefore, I have a copious supply of random numbers, copious supply pseudo-random numbers in this particular, from this. So I would like you to be able to write a simple program so that you can generate your own random numbers instead of being able to depend on mathematical software. But you can also use mathematical software, but I want you to understand what goes on within the mathematical software here. So that's the idea here. So once I know how to compute random integers, m is the maximum value. Please understand all the numbers are going to be in between 2 to the power of 31 minus 1. M is 2 to the power of 30, the modulo is 2 to the power of 31. Therefore, yn xn by m is a fraction. This fraction is such that it can be 0, but is no more is always strictly less than 1. So xn is generated by 1, yn is generated by 2. Yn is called random numbers in the interval 0 to 1. We say yn is a uniformly distributed random numbers in the interval 0 to 1. What is uniformly distributed random numbers? 0, 1. The probability density function looks like this. That's 1. The theory of random generators is very deep and is a part of simulation literature. So anybody who wants to do simulation, and this day and age, simulation is the name of the game. This is called digital twin. So you can digitally simulate anything today. So the fundamental ingredient in digital simulation is ability to generate random numbers. So first you need to generate uniformly distributed random integers, uniformly distributed random numbers in the interval 0 to 1. So what is the homework now? Generate a million random numbers and compute the million random numbers, random integers. What is that? I am going to ask you to compute u belonging to 0, 1, million of them. I am going to ask you to plot them 0 to 1, and I would like you to be able to compute the histogram and check the histogram you compute is very nearly uniform. Then compute the mean, compute the variance of these million random numbers you have generated, and you have the standard distribution 0 to 1. You can mathematically compute the mean, you can mathematically compute the variance of this distribution. So this is the population value, this is a sample based value. You compare the population value with the sample based values and check how good your estimates based on the random number generator that you used. So that's a very good exercise to start with. So random number generator for a fixed m, a and c using different initial seeds, we can generate different sets of random number sequences. So if you don't, for a fixed m, a and c, if you don't change x naught, we will generate the same device. Why? The method is deterministic. So if you want to repeat the experiments, but you can keep m, a and c fixed, you need to be able to change only x naught. I told you, telephone number, birth date. So if you want multiple sequences, you can use multiple birthdays or simply pick randomly 10-digit large 10-digit numbers as initial conditions. If you use the same x naught, we will get the same sequence. So by suitable transformation, okay, now if I have xn, I have yn. If I have yn, I can transform these numbers to obtain different families of distribution such as binomial, exponential, Poisson, Gaussian distribution. So I want to be able to simulate an arrival process. That means I want to have a Poisson. I want to have a Gaussian distribution. I want to have an exponential distribution. I want to have a binomial distribution. Of course, all these things are available in MATLAB and any other good scientific scientific package libraries. But I would like you to be able to see how those scientific libraries work so that you can understand the guts of the program. What is the basic idea of the program? So after this quick introduction to random number generator, I am going to illustrate the Monte Carlo method. I want to be able to evaluate the area under the quadrant of a circle of radius 1 inscribed in the unit square. So this is the unit square, this is the quadrant of a circle inscribed within that. The area of the unit square is 1. We already know this is the area of the quadrant is equal to 1/4 of the area of a circle of radius 1. Pi r square is equal to pi. 1/4 of pi r square is pi by 4. We already know the answer. So I am going to now talk about a method by which you can verify whether I am going to get a number which is close to pi. Now please understand pi. Do we know pi exactly? No. Pi has been evaluated. What is the problem there? Pi has a non-terminating decimal expansion. If it is non-terminating, I want to see whether it is periodic. So they have computed millions of digits in the expansion of pi to be able to verify whether it has a repeating pattern. That problem is still not quite settled. Ramanujan was one of the early pioneers in giving formulas to be able to compute pi. If you look at his notebook, last notebook, at the Indian Institute of Science Library, there is a handwritten mimeograph notes, Ramanujan's last notebooks. So if you go to the library, such good libraries, please take a look at books, handwritten version of many results by Ramanujan. And one of the things he has done is to be able to give formulas for pi. So we already know this, so we are going to use this knowledge to be able to test the quality of our algorithm. So now I'm going to be, so I know the answer, I'm going to test my program to see how good a result it gives. So what is the idea? The idea is to generate a random number pair. So you generate a random number u in the interval 0 to 1, v in the interval 0 to 1. So if I have a pair u comma v, it should be a point within the unit square. Every point within the unit square does not lie within the quadrant. Some may lie inside, some may lie outside. Now we know if u and v are such that if u square plus v square is less than or equal to 1, it lies inside the circle. If v square is greater than 1, it lies outside the circle. So you keep throwing numbers. If it's like throwing dots. If you throw a dot, either it falls inside or outside. If you threw a large number of dots, the fraction of the number of dots that falls inside to the total number of dots thrown gives you an estimate of the area under the quadrant. That's the basic idea. So the idea goes as follows. Generate a pair u comma v, uniformly distributed random numbers in the interval 0 to 1. If this pair defines a point randomly, this pair defines a point randomly within the chosen unit square. If u square plus v square is less than or equal to 1, that point lies inside the circle. Otherwise, it lies in the annulus region outside the circle but within the square. So how am I going to translate into a program? Thus, by picking a set of n pairs ui vi I is equal to 1 to n, we can determine the number m of pairs that falls within the circle. Then in the limit m by n, as n goes to infinity, capital N goes to infinity, we should be able to tell in this particular case it tends to pi by 4, not pi by 4, which is the area of one quadrant of the unit circle. The area of the full circle is pi r square, r is 1. So this must tend to pi by 4. So please understand, it's not pi, it's pi by 4. So we are trying to estimate pi by 4. If I can estimate pi by 4, I should be able to estimate pi. So we can think of this a randomized algorithm to be able to estimate pi, Monte Carlo method. So that's a very good idea to be able to get a hang of what the Monte Carlo method is all about. So here's a pseudo program. Count is 0 for I is equal to 1 to capital N. Capital N can be a million. Generate the pair u comma v. If v square plus v square less than 1, count is equal to count plus 1. That means the number of points lying inside the quadrant goes up by 1. You repeat this n times. When you get out, the value of the count divided by n is the estimate of the measure of pi. So what is the homework for you? Plot the ratio count by n by changing n. So I would like you to write a program for n is equal to 10 cubed, 10 to the power of 4, 10 to the power of 5, 10 to the power of 6. For each of these, you compute the count and plot. So I would like you to be able to plot versus n versus the estimate. So this is the experimentally determined value. What is the usual value of pi we take? 22 by 7. 22 by 7 is an approximation. In fact, I have a book, 200-page book on algorithms for computing pi. There are lots of people who spend their life in simple algorithms of this type. I don't know whether you heard this recently at the ICTS, International Centre for Theoretical Studies in Bangalore. People who are working in theoretical physics in string theory, they accidentally discovered a new formula for computing pi. So you get results from strange areas, unexpected areas. So a person working in theoretical physics, a group of people working in theoretical physics, as a result of their analysis, they were able to invent a new formula for computing pi. Look at that. That's a beautiful contribution coming from theoretical physics. So never underestimate the power of analysis. You may find good results in strange places. That's why it's very important to be able to understand, to motivate, to invigorate your interest in these areas. The value of pi is non-terminating fraction. The expansion has been known for thousands of digits and are published. I would like you to check the internet to see how many digits of pi we already know. It runs in millions. It runs in millions. So I don't want you to use a large number of digits. You use 4-digit pi, 5-digit expansion for pi. So approximate by pi by 3 times up to 5 digits divided by 4. So you get the number. You check the estimate and see how good your estimate is close to pi by 4. So that's the simulation experiment I want you to do. Now I am going to go into the second class of algorithm called Las Vegas algorithm. These two algorithms are meant to set your ideas tuned towards randomized approach as opposed to deterministic approach. Now I am going to describe a problem called Las Vegas type algorithm, again a very simple problem. These are all related to data science, but these problems are the one that helps you to capture the notion of randomized algorithms. So that's why they are important. Suppose there is a small township with a population of n persons. All the n people are eligible voters. Let us assume is a hypothetical situation. There are n people in a city. There is going to be an election for the mayor. All the n people are eligible voters and they are also eligible to stand the election. The mayor election has to be conducted in the coming in a month. Now everybody wants to run the election. If everybody wants to run an election, you can imagine no one will vote for anybody else. Since no one will vote for anybody else, the conventional method of conducting an election will not lead to any election of mayors. It's a hypothetical problem, but it's an interesting problem. It's a very thoughtful problem. It's a difficult problem. So a little reflection tells you the conventional deterministic method of conducting an election where few people contend for the post, where the large group of people vote and the person who gets the maximum vote is the winner. That's the rule for election. But here everybody runs, everybody will vote only for themselves, nobody will vote for others. So the conventional method will not work. In such case, how do you conduct an election? Babai invented a Las Vegas type algorithm, a Las Vegas type randomized algorithm. Come to a rescue. So what is the idea? The town hires an external consultant to conduct the election because no one believes anybody else in the city. They think that if anyone conducts the election, they will screw it up favoring themselves. So they agree to hire a consultant outside of the township and want him to conduct an election so that sooner or later a mayor can take the oath of office and try to run the city or the township. So the consultant comes with an idea, that the idea of Las Vegas algorithm. The consultant brings with him n copies of a computing machine where he has loaded a random number generator that can generate random numbers. This must be capital, I'm sorry, that's right. N, the little n is the number of people in the town. He has loaded a program that can generate numbers in the range 1 to n for any n greater than n. Any n greater than n, little n is the number of people, capital N is more than the number of people. So he has a computer with a program that can generate random numbers in the range 1 to n. Let us say in the range 1 to n. So he brings n copies of the program, n copies of the computer. He loads the same program in every machine and gives a copy to all the people. So what does he do? He calls them on the election day to assemble in a local stadium. He gives a copy of one computing machine to everybody and asks them to take their assigned seat. So you understand the scenario. He brings n computers, each loaded with one program that can generate numbers from 0 to little n, where little n is the number of members in the city and they would like to be able to compete in the election. So, he has to devise a method such that it is open, it is fair. In the end, everybody accepts the leader whomever the process elects. So, there should be no hanky-panky. So, everybody trusts the consultant is open, he describes the method to everybody. So, everybody understands. None of the people who are voting, who are involved in the election has anything to do with the program, nor the computers. They only are going to execute what the consultant is going to ask them to do, and nothing is not known to anybody, not known to anybody. That means everybody knows everything. So, the election goes in stages. So, what is the protocol? The election protocol. The election is conducted in cycles. Step 1. He asks everyone, please press the button to generate a random number uniformly in the interval 0 to n, where n is the number of people in the town who want to be competing the election. If I generate a random number in the interval 0 to n, different people will get different numbers provided they pick different initial conditions. So, he asks everybody to enter their birth date as the initial condition. Assuming no two people have the same birthday, they are going to generate random numbers. The numbers are going to be in the interval 0 to 1, and he tells, if you get the number 1, you stay in the election. If you did not get the number 1, you get out. You cannot continue for the next round. Please understand the rule. So, everyone has the equal chance of getting 1 or any other number. Everybody has an equal chance of getting any number from 1 to n. So, he simply picked 1 as a reference number. He could have picked any number as a reference number. With the loss of generality, let us assume 1 is the reference number that the consultant has picked. So, he says, enter, generate a random number, you register the random number, tell me if you got 1. If you got 1, raise your hand, stay in the game. If you did not get 1, please leave the computer in your seat, get out of the seats and come into a common place in the stadium. They cannot take part in the election the next step. Since the generator is fair, because it is uniformly random number generator, uniform, everybody has an equal chance, so the process is totally democratic, so it's a fair game. It generates numbers uniformly in the interval, so everybody has the same chance. The probability of anybody getting 1 is 1 over n, where n is the total number of people, which is again fixed. This guarantees that there is no bias. So, there is no bias, it is fair, it is open, everybody can accept it. So, this is what is called randomized protocol for conducting the election. Now, let us see what is step 2. In step 2, the consultant counts all those who have gotten 1. Let n1 be the number of people in this group, and clearly n1 is the least value of n1 can take is 1, the maximum value of n1 can take is n. So, let us consider, if n1 is 1, at the end of the first round I have conducted the election, I have chosen the mayor. If n1 is equal to n, no one got 1, so I got to repeat. So, let n1 be the number of people who are going to stay in the game. If n1 is 1, we have a winner. If n1 is greater than 1, we have to go to the next round. So, he counts the number of people who got 1, then he asks them individually, please set your upper bound for the random number generator, change n to n1. So, there are people to help. The consultant brings a group of software specialists to be able to help them to be able to change the range instead of 1 to n, 1 to n1. Now, clearly, every number in between in 1 to n1 can be obtained with the same probability 1 to n1. Therefore, anyone can obtain 1 with a probability of 1 over n1. So now he says in the second round, all those n1 people press the button, see whether you get 1. If you get 1, you remain in the game. All the others, please step aside. Let n2 be the number of people where n2 is greater than or equal to 1, less than or equal to n1, be the number of folks still staying in the race. Now you get the idea of the iterative process. This protocol is continued until we get a stage where there is only one person who gets the number 1, at which stage the election ends successfully. Now we told what is the definition of Las Vegas algorithm. When it ends, it gives the correct result, but it may take long to get the end. So it is clear that it may take a large number of rounds to get a leader, but eventually we will get 1. So that's the randomization. Please understand, this is a randomized algorithm to solve a problem for which there is no deterministic solution in the classical sense of the word conducting an election. So the question is, what is the average number of rounds needed to elect a leader in this protocol? So the outcome is random. n1 is less than n, greater than 1, but the value of n1 is random. The value of n2 is random. So please understand, the rules of the games are fixed. The evolution is random. They are using the random number generator on which has the desired property, and I know how, and you all know how to compute how to generate random numbers now. So what is that? I'm going to do a little bit of mathematics to be able to compute the average number of rounds needed to elect a leader. Let Ln be the average number of rounds needed to elect a leader in a city with a population of little n. This Ln is a random variable. It can take the value 1 with a probability p n1. What is p n1? Out of the n people, only one person got the 1. So what is the probability? Out of n people, j people will get 1. The probability anyone can get a 1 is 1 over n. No one gets a 1 is this is 1 over, I'm sorry, this must be 1 minus 1 over n to the power n minus j. So this is the binomial probability. What is that? Out of n tosses, I get k heads. Out of n people, j people get 1. So I'm trying to fit a binomial model to compute my probability. So the probability that j out of n folks will generate the number 1, that is p and j. So p1n, p10, p1j. So the L1 takes the value 1 with the probability p and 1. If j is 0, I spent 1 round, but I have not found any reader, so I am going to have to consider an average Ln. So L1 is equal to 1 plus Ln with the probability p of n0. So this is called steady state analysis. In queuing theory, this kinds of analysis is very popular. After the end, j people got it, so I have to, the Ln takes the value 1 plus Lj with the probability p and j. So the average is essentially multiply the value with the probability, multiply the value with the probability, multiply the value with the probability, add them all. The probability is given by this distribution. So I'm fitting a simple binomial model to do that. Thus, Ln is equal to 1 times p and 1 plus 1 plus Ln p and 0 plus j is equal to 2 Tn Lj p and j. You simplify this formula, you get 1 plus Ln p and 0 plus j is equal to 2 Tn Lj p and j. That's a very simple arithmetic. I want you to be able to check this. So this is a recurrence relation. Ln is expressed in terms of Ln and Lj. For example, in the case of Fibonacci recurrence, f of n is equal to f of n minus 1 plus f of n minus 2. T of n is equal to t of n by 2 plus n. So this is called the first order occurrence. This is called the second order occurrence. Why? In the first order occurrence, n depends on n by 2, only one instance in the past. In this recurrence, n depends on n minus 1 and n minus 2. So this is called second order occurrence. In here, ln depends on ln minus 1, n minus 2, all the way up to L2. So 2, 3, j plus 1, j minus 1, L depends on all the things. So that means L depends on the entire past. So this is called complete history equation. Complete history recurrence. First order recurrence, second order recurrence, complete history recurrence. Therefore, L is defined in terms of itself recursively, and L depends on all the values of the past. So if I took ln, all the ln to one side, all the lj, j less than n to the other side, I can express 7 in terms of a very nice recursive term. Ln is equal to the numerator, denominator is a constant, please understand, 1 minus p and 0. P and 0 I can compute, p and n I can compute. I have a formula. So denominator is a constant. The numerator depends on lj, j from 2 to n minus 1. So ln depends on ln minus 1, ln minus 2, L3, L2, complete history. So I have to solve this equation. Please understand, mathematically solving this equation is challenging. I want you to ask yourself the following question: how do I solve first order occurrences? How do I solve second order occurrences? Please understand, these are parts of the discrete mathematics that comes into play in computer science and data science when you want to be able to characterize the behavior properties of algorithms. These are part of discrete mathematics, for those of you who may not have had an occasion to talk about that. So there are excellent books on discrete mathematics. So if you want to be a good data scientist, please get a hold of a very good book on discrete mathematics, a good book on probability theory, a book on statistics, a good book on matrices, a good book on linear algebra, a good book on programming, a good book on numerical analysis. I can't overemphasize the need for having a good reference book in your own shelf, in your own personal library. Okay, now I want you to be able to solve this equation. I want you to be able to solve this equation. So what is L1? In a city with only one person, there is no need to conduct election. So the average number of rounds is L1, L1 is 0. Are you with me? So what is L2? What is L3? So I would, given this is the boundary condition, I can compute recursively. Given L1 is 0, I compute L2, compute L1 and L2, compute L3. So you can compute this numerically and plot this versus n. So Ln versus n, that gives you the actual number, that is the solution of 8. So I can evaluate numerically. I also would like to be able to evaluate in closed form. So numerical solution, closed form solution. Now I am not going to do either of them. Plotting numerically is a homework problem for you. These are all very good homework problems for you to be able to improve your understanding of discrete mathematics and interaction with algorithm analysis. It can be shown, it is obvious, Ln depends on Lj for j is equal to n minus 1. It is a complete history recurrence. Now I am going to quote a result from Babai's paper. He showed by asymptotic analysis Ln is less than E, and what is E? E is the Neperian base, is 2.718 for all n. Wow, that's an astonishingly important result. And an average, independent of n, the total number of rounds that you need to do is no more than 3. So is less than 2.71. That means, so if you conduct this election, irrespective of how large the population of the city, I should be able to get the leader in no more than 3 rounds on an average. That's a remarkable result. Also, I can compute the exact solution and compute the limit. The limit is essentially 2.442. The exact limit is less than the approximation. So, this is an upper bound, this is a limit. Therefore, Ln is less than 3 for all n greater than or equal to 2, greater than or equal to 2. L is equal to 1 is not interesting. L is equal to 2 or more is interesting. So, on the average, one needs only 3 rounds even for large n. Now, you see the power of a randomized algorithm. I am able to solve a problem very simply, and I am able to give you an exact solution where the total number of steps on an average is no more than 3 finite. If the average is finite, you would, so I have a random variable, L is a random variable, right? I'm sorry, L is not random, L is the, I misspoke, I'm sorry. L is the average number of rounds. So, if a random variable is such that the average is finite, you would expect high probability. For example, if you have a normal distribution which goes from minus infinity to plus infinity, in principle it can take very large value, but it takes very large value with a very small probability. That means a normal random variable taking very large value is very rare. That's the impact of saying the mean is finite, the mean is less than 3, the mean is 0, and so on. Therefore, in some experimental runs, you may have smaller number of cycles. In some election, there may have larger number of cycles, but on an average is no more than 3. So, I would like you to now talk about homework problem. Plot P and J. I already told you P and J. P and J is the binomial probability where P is equal to 1 over n. Plot P and J for n is equal to 10, 100. What is this? This is P n k, 1 over n to the power k, 1 minus 1 over n to the power n minus k. So, let us assume n is 10, k runs from 0 to n is 10, n is 100. Please plot this. You already know NCK p to the power k 1 minus p to the power n minus k is the binomial distribution, is the same as that. When p is half, this becomes NCK 1 over 2 to the power k, this is 1 over 2 to the power n minus k, this is equal to NCK times 1 over 2 to the power of n. So, I would like you to be able to plot this with k is equal to half, plot this with p is equal to 0.3, p is equal to 0.7. Here p is much smaller, 1 over n. So, try to see whether the function is symmetric when the function is like this or when the function is like this. So, this is symmetric, this is left skewed, this is skewed to the left, this is skewed to the right. So, by plotting this, you get an idea of for what values of p it gets skewed to the right, for what values of p it gets skewed to the left. Also, compute and plot Ln as a function of n for n 2 to 50, for n 2 to 50. And I would like you to be able to compute L2 as a homework problem. If there are only 2 people, how will you conduct an election? Head or tail. So, head comes, so if there are 2 people A and B running in an election, head or tail, if head comes in, the coin as a fair coin, if a head comes A wins, if a tail comes B wins. So, L of 1 is 0. That means if there is one person, no election needed. He is already the king. If there are two people, I need to conduct the election in one step by simply tossing a coin. So the initial condition L1 is 0, L2 is 1, given L2 is 1, compute L3, given L2 and L3, compute L4. So that is a numerical problem, that is a numerical problem, plotting problem. So with this, I believe I have given you a very good idea of randomized algorithm. The reference for this is the paper by Itoy and Roda, symmetry breaking in distributed networks. Please understand this as symmetry breaking. I would like to talk about symmetry breaking in for a few minutes now. So suppose there are two champions wanting to play a chess game. There's an umpire. How do you decide who starts the game first? You toss a coin. The umpire tosses a coin. You ask him. You call. I am going to toss. You call. Head or tail. The coin. Whomever calls head is going to be starting. So starting of any football game, any game, parallel game, is going to be decided by tossing a coin. So that's what's called symmetry breaking. Anybody could start. Both the people want to start. Whom do you ask to start first? So there is a symmetry between two players. I want to break the symmetry. I want to be able to break the symmetry by consulting a random number generator by tossing a coin. And that's the usual way we do. I'm sure you all have heard from Bible the story of Solomon. You remember the story? He will sell. There are two people who are competing for the child, claiming their own child, and he said, well, if both the people want to claim the child, cut the child into two pieces and give each piece to one. The true mother at that time came out saying that even if I didn't get my child, I want the child to be alive, so please don't cut it. So the truth came. That's called the Solomon rule. Solomon rule is essentially symmetry breaking. I'm sure you have heard this fairy tale, Solomon's rule. So Solomon's rule is a fairy tale related to symmetry breaking. Tossing a coin to start any game is symmetry breaking. Now, what is that we are talking about symmetry breaking here? In an election, there are n people, everybody is eligible, everybody is equally qualified. That's total symmetry among all of them. Everybody can do a job. How do you break the symmetry? We don't have a coin with n sides, so we had to emulate the coin with n sides. How did we emulate the coin with n sides? Using a random number generator that can generate random numbers from 1 to n. So by converting the standard approach by causing tossing to a general random number generator, we were able to break the symmetry involved in the election, leading to what's called Las Vegas type algorithm. So in summary, randomization is used to solve difficult problems. Randomization helps to compute the solution in a faster way. Monte Carlo method always provides a good but approximate solution. The quality of approximation improves with the size of the samples used. Las Vegas algorithm, on the other hand, when it stops, it gives the correct answer, but you may have to wait a little longer to be able to get the answer at all. So in the Las Vegas type algorithms, you have to worry about what is the average number of samples, average number of rounds needed to be able to get the right result. I hope with this it provides you a good background on the basic aspects of random number generator, philosophy of randomness. With this as a background, now we are going to transition into talking about randomized algorithms for linear algebraic problems. Thank you.